All right, so today we're doing day 6, which is your undefined derivatives. So since we already know that the first derivative represents the slope of a tangent line, the derivative would be undefined whenever we can't be sure about the placement of your tangent line. Okay, so how does this happen? So we're going to explore the different times when this would be the case. All right, so first example we look at is f of x equals 1 over x. If we look at the graph of that, f of x equals 1 over x, you may remember, first off, there's a vertical asymptote at x equals 0. You would have the point 1, 1, 2, 1/2. All right, and then you'd have a matching part of the hyperbola down there. Okay, so that would be your f of x equals 1 over x. All right, so now let's look at the derivative. So first off, let's rewrite f of x. Instead of 1 over x, that's really x to the negative first. We can use our rules from yesterday. All right, so this would mean that your derivative, the first derivative of x, would be, bring down your exponent, so negative 1 x to the negative second. So if we rewrite that, the derivative of f of x would be negative 1 over x squared. And we know that that would be undefined when x is 0. All right, so the derivative of f of x at 0 is undefined. That means you would not be able to come up with the slope of your tangent line because there is nowhere to place it. Okay, but if you look at this graph, all right, what do we notice about the graph at 0? Well, at x equals 0, there's a vertical asymptote. And that means your graph is not continuous at x equals 0. So that's going to be something you're going to want to keep in mind. All right, so let me write something here. So f of x is not differentiable at x equals 0. Okay, because we cannot define your derivative at 0, that means it's not differentiable at 0. And it says, for what value of x is this the equation for your derivative undefined? Well, that's at 0. What do you notice about the graph? F of x is discontinuous at x equals 0. So that'll be something you notice when we look at graphs. If your graph is not continuous at a specific value, then your derivative would not exist. It would be not differentiable at that same value because you would have nowhere to place that tangent line. All right, let's look at another one. So f of x equals absolute value of x. So absolute value of x comes to a point at 0 and goes out each direction. Now, I'm going to rewrite this in a different way as a piecewise because we got to look at it from the different sides. So if you come on the left-hand side here, f of x is really negative x, right? It would be y equals negative x, that linear equation when x is less than 0. And f of x would be x when x is greater than or equal to 0. And you could put 0 on either part of that as long as one of them is a less than or greater than, the other one is the less than or equal to or greater than or equal to. Just because they are two different lines there. All right, so let's explore the derivative at x equals 0. Here's your limit definition of a derivative, which we did the first few days. All right, so the limit as h goes to 0 of f of x plus h minus f of x over h. If you input your absolute value, it comes down to this. So remember, this is your slope function of your tangent lines. All right, well, if we put in 0 here, absolute value of 0 is 0 over 0, this is the indeterminate form. Okay, we've already done that. So we have to look at it a little differently. It says approach 0 from the right and the left. So back up to our piecewise. If we approach from the left, let's make the first one from the left, the derivative at 0. Well, if we're coming from the left, that's this negative slope one, we'd be looking at f of x equals negative x. So if I use my tangent slope function here, it says the absolute value of h, well, if you're coming from the left, absolute value of h is h, doesn't matter. But if we're coming from the left, on the denominator where that says h, those would be negatives. So you'd have h over negative h, which is negative 1. So from the left, your derivative at 0 would be negative 1. If we come from the right, now we're looking at a positive sloped line. So we're looking at f of x equals x. And if we use our tangent slope function here, you would end up with h over, this time h would be positive on the right-hand side. So that would become 1. And what do we know about when they're both not the same here? That would mean that your derivative at 0 would not exist. All right. Now, this is not one where it's not continuous, but what do you notice about the graph at 0? Well, because there is a sharp corner, okay, if there's a sharp corner, then f of x is not differentiable. Okay, so if it's not continuous or there's a sharp corner on the graph, you can't figure out where to place that tangent line. Thus, you can't find the slope of it, which is the first derivative. All right, so conclusions on those two examples that we just did. If a function is discontinuous at a point, then the derivative is undefined at that same point. Or if the graph of your function has a sharp corner at a point, then the derivative is undefined at that point. Okay, so those are the two cases that we just looked at. If your graph is discontinuous or has a sharp corner, then you know at that point the derivative is undefined. All right, so you'll see that showing up. That's evident in this first one here. So we're looking at f of x is the absolute value of x minus 2. Notice we have that sharp corner. So because there is a sharp corner, the derivative at 2 does not exist. Okay, so that means f of x is not differentiable at x equals 2. All right, well, if you look at the next graph, there's no sharp corners and it's not discontinuous. Okay, but this one's got a different issue. So let's look at the function here. We've got f of x equals x to the 1/3. If we find the derivative, it would become 1/3 x to the, if I subtract 1, negative 2/3, which really means I'm looking at 1/3, and that would be the cubed root of x squared. So x cannot be 0, right? Because you got x in the denominator, x can't be 0. Well, what do you notice about the graph at 0? You would end up, if you drew in your tangent lines, it would actually end up being a vertical tangent at x equals 0. And what do we know about vertical lines and their slopes? They're not defined. Okay, so if you would have a vertical tangent at any point on your graph of f of x, then you would not be differentiable. So the derivative does not exist at 0. All right, so another case to add into this: discontinuous, any vertical tangents, or sharp corners. All right, here we're just making sense of some statements based on differentiability. So there's a theorem that says if f is differentiable, then f is continuous. Well, that's got to be a true statement, okay? Because if you have something that is discontinuous, it's not differentiable. All right. So if you know it's differentiable, then it had to be continuous. All right. And that actually goes down to the bottom here, the contrapositive. If f is not continuous, then it is not differentiable. That's also true. Okay. That's that statement we made up top. All right. What about these two middle statements? If f is continuous, then f is differentiable. Not everywhere, because in the case of a sharp corner, that's continuous, but it's not differentiable. So that's a false statement. Okay, just trying to make sure we understand the difference between continuous and differentiable and when they go hand in hand. If f is not differentiable, then it's not continuous. Well, not true. Same case, right? That's not differentiable, but it is continuous. Okay, so that's also a false statement. I wouldn't worry too much about those, just kind of making sense here, but it's really more, can you look at a graph and understand what's going on in an equation, what's going on? All right, so just some examples now using them and seeing them either with an equation or with a graph. It says state the values of x for which the function has an undefined derivative. So whether it's discontinuous or you don't know where to draw a tangent line, there's a sharp corner, there's a vertical tangent. All right, so we've got y equals the square root of x plus 4. Well, let's think about your derivative. So first off, the square root could be represented as a power of 1/2. So if we're coming up with the derivative, it'll be 1/2 times x plus 4 to the now negative 1/2, which really means that it is 1/2 times x plus 4 to the 1/2. All right, and looking at that, because you got the denominator where the variable is, x cannot be -4 or it makes the denominator 0 and so forth. So x can't be -4, then that would mean the value for x where it's undefined derivative, that would be our case. So at x equals 4, f of x is not differentiable. Let's look at a graph. So if you remember what radical functions look like, they have a starting point and then they go off, and that starting point would be from that horizontal shift to the left. So at -4, well, where's your tangent line going? Okay, because it comes in and comes to a stop. It's not continuous there, it starts there. All right, so it is not differentiable. All right, let's look at the next one. F of x equals 2/10 plus x. Well, let's look at the derivative. We'll have 2 times 10 plus x to the negative first. If we come up with the derivative, it'll now be -2 times 10 plus x to the negative second, which if we rewrite that, it'll be -2/10 plus x squared, and x can't be, in this case, -10. So at x equals -10, f of x would be not differentiable. All right, and let's look at a graph of it and understand why. So this would be a hyperbola, right? It's a rational function. You would have a vertical asymptote here at x equals -10. Something along those lines. All right, and because you got that vertical asymptote, your graph is not continuous at x equals -10. Okay, so looking at the graph, looking at the function, coming up with some ideas of how you can explore if a function is differentiable or if it has a defined derivative or not. All right, here we have no function rule. We're just looking straight at a graph. Where is this not going to have a defined derivative? Well, we know that if it's not continuous, then we know we have an undefined derivative. So where on here do we have our graph not being continuous? Well, not continuous over here at -2, right? There's a jump break in the graph. So at x equals -2. Also not continuous at x equals 2 because there's a vertical asymptote. Also not continuous at x equals 3 because of the point of discontinuity there. All right, and then that's where we have the discontinuity. What else is on this graph that makes it not differentiable? That sharp corner. So you have a sharp corner at x equals -1, meaning you would not be able to come up with your derivative. It would not exist. Okay, and then just kind of showing you graphs of your different cases. What destroys differentiability? So anytime you have a sharp corner, make it look like an absolute value graph, or a cusp, which is closely related to your sharp corner. It just comes in rounded and bounces out, but it still has that sharp peak there. All right, so if you're looking at a graph and you see a sharp corner or a cusp, not differentiable. All right, we know the vertical tangent case. That's where it comes in, flattens out vertically. Okay, so here's where we run into that issue. Anytime we have a vertical tangent. And then you've got your discontinuity, which we explored in the last unit, but we'll just recap real quick. All right, discontinuity comes when you have a vertical asymptote. All right, so just throw a vertical asymptote on there. Okay, anytime you have a vertical asymptote, discontinuity. All right, if you have any points of discontinuity, so that's where your function goes along, boom, hole. Okay, and then you've got the point up here someplace, discontinuous. Or if you've got your jump break, meaning you come in from one side, but then it jumps up and continues off that way. So that's discontinuous. All right, so you've got some practice problems there. Delta math. Come with questions.